Okay, everybody, welcome to the first epidemiology seminar of the year. Could someone close the door? Thank you. Because we will be loud and I'm loud. All right, so this is a Monday epidemiology seminar, and I'm Hiroshi, as most of you know, and I'm coordinating this seminar. First, I'd like to start with land acknowledgements. McGill University is located in the traditional and unceded territory of diverse indigenous people, including Haudenosaunee and Anishinaabe people. And we'd like to thank their presence, which marked the land we learn and exchange today. So I'm just gonna give this is first talk, so give very quick housekeeping information for, in particular, first year students. So we have a seminar regular basis, as you know, but not every Monday. So please check schedule. Number two, around 5 seminars are shared between epidemiology and core Center for Outcome and Evaluation. That's not in this site. So we often stream into 2 sites. Sometimes we have in-person speaker. Sometimes we have a virtual talk, just like now. And this is the very first joint seminar with core. So just a heads up, like some talk will be virtual, but if we are here, there will be always a hybrid talk, meaning that we will stream talks. And number 3, so I think you are informed about attendance sheet, so please check if you attend the seminar. And number 4, there seems some misinformation that we get cookie and coffee for this, but that's mostly for biostatistics. But we will try to get cookie and coffee for epidemiology seminar too, if budget allows. So that's basically it for housekeeping. You know the schedule of our seminar. Before I will let's pass to Dr. Nandi Dendukri, who is on other core site, I'll just quickly say that we will take questions after the talk, after Dr. Denis Nash's talk, and we will take questions. So you're allowed to have a question after the talk, as well as the people on Zoom. And if you have any question, you please also write on the chat room. So we will take question from core and our site as well as chat. So that's basically it. So I will pass to Nandini for the introduction of Dr. Denis Nash. Please go ahead, Nandini.
Thank you. Thank you so much, Hiroshi. I'm delighted to introduce to all of you today Dr. Denis Nash. Denis is a distinguished professor of epidemiology at the CUNY School of Public Health in New York. And I thought he's the perfect person with whom to begin our 24-25 seminar series, especially this particular session, which is our first joint session with EBOH, core EBOH. And Denis' background caught my eye because his interests are so close to our own interests here across these 2 units, core and EBOH. Denis brings a wealth of knowledge in infectious diseases epidemiology, implementation science, public health surveillance, and he's done some large studies involving electronic medical records in international settings. That must have been interesting. It's complex enough doing it in one jurisdiction. I'm curious how you handle that in an international setting. In particular, I was intrigued by the fact that he's the executive director of CUNY's Interdisciplinary Institute for Implementation Science in Population Health. There's not a lot of institutes of implementation science that I'm aware of. All in all, I thought Denis would make a great speaker for us here today, and I'll pass the floor over to you, Denis. Thank you so much for agreeing to be with us today.
Thanks so much, Nandini. Thanks so much, Hiroshi. It's great to be here. And I'm coming from my own department, which is a a combined Department of Epidemiology and Biostatistics, which I and my colleagues there really love. It sounds like you guys at McGill are working closely together as well, bridging the disciplines, which I think is where some of the best work is coming from. And you'll see, I mean, we have a lot of collaborations between our two disciplines as part of this work that I'm going to talk about today. So let me see if I can get my slides started here. So these are my disclosures. And here's just a quick overview of what I'll be covering in the presentation. First, I want to start with like a brief introduction of the IeDEA Cohort Collaboration to give you some context on this global network's reach and the scope of the data we're working with. And then I want to talk about the emergence and evolution of the use of quasi-experimental methods in the IeDEA network. And we leverage these methods to assess the impact of treatment guideline expansions for HIV and the effect of treat all policies on HIV care outcomes. And this will help frame our thinking around some of the approaches that we're planning to use to assess the causal impact of extreme weather on HIV care outcomes. And then after that, I'll shift a little bit to the climate related research that we're starting in IeDEA with some background on the ways in which we think extreme weather events may influence HIV outcomes. And then finally, I'll introduce our latest study on this, the Weathering HIV study. I'll talk about its aims, its design, methods, and some early data. And this should hopefully give you a sense of where we're headed in terms of understanding the impact of extreme weather on HIV outcomes. So just to provide a little context and background, this slide shows some of the global progress that we've made against the HIV pandemic, largely through the use of antiretroviral therapy, or ART, as I'll refer to throughout the presentation. On the left, it's showing here the number of deaths that are due to HIV/AIDS in red. This would be what would have happened without the large scale up of antiretroviral treatment that really began in the places around the world that were hardest hit in 2003 and 2004. And here on the right, more recently, we're showing here that the burden of deaths due to HIV is greatest in sub-Saharan Africa. And to put some numbers on it, today we have about 38 or 39 people living with HIV. This number is going up because of survival due to treatment, but it's also going up because we have about 1.5 million new cases, new infections that occur every year, and about 800,000 deaths per year, as you can see, down from about 2 million at the peak. So basically the scale up of antiretroviral therapy has averted tens of millions of deaths, but we still have a long way to go with very large numbers of deaths due to HIV still occurring today. And this is a slide to tell you about the global IeDEA Cohort Collaboration, which I'll be talking about a lot today. IeDEA is a network of cohorts of people with HIV enrolling in care all around the world. There are 7 regional cohort collaborations, including 4 in sub-Saharan Africa, 1 in the Asia Pacific region, 1 in the Caribbean and Central and South American region, and then 1 in the North American region. So to date, and it started collecting data back in 2004, about 2.3 million patients have enrolled in HIV care at IeDEA participating sites. It's more than 700 clinics from 44 countries around the world. And as I mentioned, data going back in some instances all the way to 2004 and is ongoing today. And funding is from the US NIH. And in addition, I just want to highlight some of the depth in the IeDEA network about as it relates to research expertise that cuts across IeDEA in the form of scientific interest groups or scientific working groups that specialize in things like pediatrics, tuberculosis, mental health, and substance use, and so forth. And to give you an idea of the kinds of data we collected, Nandini, as you alluded to before, it's very complicated. We had to come up with our own data exchange standard, and I'm putting the reference in here of a paper that Stephanie Duda and others in our in our collaboration have published describing how we harmonize and exchange data from disparate sources and formats across so many different settings. But this is largely, the cohort data largely is comprised of data that you would find in medical records. There's not patient interviews or patient self-reported information. It's things like visit dates, medications, lab tests, new diagnoses, pregnancy status, and things like that. So I wanted to now describe the process of how we've been using quasi-experimental methods in IDEA and show some examples. Of course, this is relevant to extreme weather, and we'll get to that. But and also just to keep it interesting, I did attempt to create some relevant images with artificial intelligence throughout. These have had sort of mixed results, sometimes odd results. But it's my first time, so be patient with me. For example, I asked for an image conveying regression discontinuity, and it gave me back something like regression discontinuity. I can't really tell what it says, but anyway, you get the idea. So the first use of quasi-experimental methods in IDEA sort of came about when we began to try to characterize the impact of, when my team started to try to characterize the impact of HIV treatment guideline expansion on care outcomes. So the World Health Organization sort of progressively over the years expanded HIV treatment eligibility, first really only limiting treatment to the very sick, those with very low CD4 counts, and then progressively expanded to higher and higher CD4 counts, such that by 2015, the World Health Organization finally recommended treating all people with HIV, regardless of their stage of illness and CD4 counts. So we were very interested in this guideline expansion. We were particularly interested in how treat all policies were impacting HIV care outcomes. So we also knew that when people would show up, for example, in 2009 with CD4 counts above 350, they would hear they weren't eligible for treatment yet, and they'd have the recommendation would be to come back for regular evaluations, and eventually, when they became sick enough, they could start treatment. In fact, what happened is a lot of people were lost to care prior to becoming eligible for treatment. And so one of the reasons we're interested in understanding the effect of these guidelines expansions is to see if it improved things like retention and care. But there's, of course, also a risk that we were aware of that guideline expansion could have some negative impacts. For example, if it crowds out people, if healthier people are now more eligible for treatment, is it crowding out people who were sicker than them while the guidelines are expanding? So these were sort of setting the stage for this work. As I mentioned, we really were interested in looking at the treat all policy expansion specifically, but while we were waiting for those data to come online and be available, we decided we would start by looking at some of the earlier guideline expansions. So we looked at these first two expansions when it went from 200 to 350 and 350 to 500 in this paper. And I wanted to present this analysis because it really represents like the gateway paper that led to our use of quasi-experimental methods, but it isn't quite an example of quasi-experimental methods, and I'll explain why. You'll see why in a minute. So to assess the influence of guideline expansion on the outcome of interest for us was like how soon, the timeliness of treatment initiation after enrollment. We used data from IDEA on about 240,000 patients that enrolled in care in 21 countries where these guidelines expanded in our data set. So that was about 21 countries out of the 40 countries represented in IDEA that we ended up focusing on. And the first analysis was looking at expansion to 350, and that was about 167,000 patients. And the second analysis was expansion to 500, which is about 73,000 patients. And this just gives you a sense of the geographic breadth of the countries that were included in the analysis. So I just want to start by saying I was not trained when I did my epidemiology doctorate at PhD on quasi-experimental methods, and we were only beginning to introduce these kinds of methods to our doctoral students at the CUNY doctoral program, and so without that sort of background, this was the design that we came up with to look at the impact of this guideline expansion. So we basically created a buffer period. We had a time zero, which was the date of the guideline expansion, and we had a buffer of 6 months before and 6 months after that we sort of the data we sort of ignored, and then we calculated an estimate of the timeliness of treatment initiation. In this case, it was the proportion of people coming in care that that initiated treatment within 6 months. And we calculated that same estimate for this latter period, the cumulative incidence of ART initiation within 6 months. And then the outcome for each site was basically the difference between the post cumulative incidence of ART initiation within 6 months minus the pre-period. And we kind of put this together in a meta-analysis type of thing. So each one of these dots here represents that calculation I just showed, the pre-post difference for a given site in the cumulative incidence of timely treatment initiation after minus that before. And so you can see the 136 sites that were sort of arrayed here, their individual estimates and the overall pooled effect here for the analysis. And you can see it was a small but significant effect. About 3.8% more people initiated treatment within 6 months following the guideline expansion. And there was a range. And we also noticed that those people that were newly eligible under the new guidelines had a larger effect than that of the overall effect. But we didn't see any change among those who were previously eligible, so there didn't seem to be a crowding out effect. And we also didn't see any appreciable difference by sex or age. Now, this slide is showing the next guideline expansion going from 350 to 500. And in this analysis, same design, we saw a much larger effect. So it was about almost 17% difference in the proportion in the cumulative incidence of timely treatment initiation after the guideline expansion. So it suggests that patients were starting treatment more quickly after the guideline expansions. And in this case, we were seeing, large effects again among those who were newly eligible under the guidelines. We did see some sex differences here, such that women had even higher changes in the incidence of timely treatment initiation, as did patients who were age 16 to 25, and very small changes in those who were previously eligible under the guidelines. But again, it didn't go down, it went up. And this is just sort of graphically showing that we were seeing in both of those analyses larger differences among those who became newly eligible as part of the guideline expansion, and not so much of a difference for those that were previously eligible. So sort of what we would expect. So in conclusion, these analyses strongly suggested that the expansion of HIV treatment guidelines had a significant positive effect on the timeliness of treatment initiation, particularly among those who became newly eligible. These analyses, though, were completed in 2016 and 2017. And I guess I want to highlight here that when it was being reviewed at PLOS Medicine, I later learned our academic editor was Mary Louise Newell, and our peer reviewers were Jacob Bohr and Till Barnickhausen, who many of you may know from some of their work on quasi-experimental methods. And they particularly, as part of this great review, I have to say it was one of the most engaging peer review processes that we've gone through. It really did, while they supported the strengthening of the approach that we did take, we also talked a lot about, other designs, such as regression discontinuity, that might be appropriate, and learned about this paper that made us more aware of these methods and also how to apply it. So the lead author on this paper was one of our epidemiology doctoral students, Olga Tomaichik. she suggested when we move into the treat all analysis that we might try this method, this regression discontinuity method. And so finally, our data became available that we were waiting for. It was after the treat all policy expansion. Just to remind everybody, that this was something that by mid-2017, almost every country around the world and almost every country in IDEA had passed national treat all policies. And we had data that would allow us to ask questions like, did national treat all policies improve timely ART initiation? And also, was there an impact on care retention? And so our epidemiology doctoral student, Olga Tomajczyk, led us through this analysis, which was now moving from our approach that I walked you through design into our first application of a quasi-experimental design in the IDEA network. And so this analysis focused on 6 countries where treatment guidelines expanded to treat all people with HIV. And it was 6 countries in sub-Saharan Africa. We had data on about 800,000 adult ART-naive patients that enrolled in care over this entire time period. So that allowed us, you'll see in our graphs, to be able to look at not just the treat all expansion, but the other earlier ones as well. Our outcome changed from ART initiation within 6 months to within 30 days because the treat all guidelines were recommended ART initiation within 7 days. That was the WHO recommendation. So this is truly a timely ART initiation outcome. And we used regression discontinuity design, which is looking for discontinuity at the threshold of the date of the national treat all policy. And it allows for looking at the differences in slopes before and after the policy changes as well. So it's regression discontinuity in time. We use data-driven bandwidths to estimate the predicted outcomes and risk differences at the threshold date. And as many of you probably know, this design takes advantage of the local randomness around a cutoff that basically creates exchangeability, allowing for a causal interpretation of the observed effects. And so of the 6 countries, they kind of fell into 2 large patterns. Here I'm showing you Rwanda, Kenya, and Burundi. And each of the green lines represents earlier guideline expansions. And what you can see was a very dramatic effect at the treat all guideline threshold in 2016 in Rwanda, such that there was a big jump in the proportion starting treatment rapidly, as well as an increase in the slope. And this was a similar pattern that we observed in Kenya and also Burundi. And then a slightly different pattern in some of the other 2 countries, but still an effect observed. Here I'm showing you Malawi, Zambia, and Uganda. And basically here, this is actually more similar to the earlier ones, a jump and then an increase in slope. But here in the other 2, we pretty much see an increase in slope at the treatment threshold, not necessarily a jump in the proportion or in the intercept. We've also gone on to use other types of quasi-experimental methods, and this is an example of a study led by John Ross, who examined the impact of treat all policies on timely treatment initiation in Rwanda, and also retention care. But unlike the prior analysis, this one used interrupted time series. And here we were assessing whether there were changes in the intercept and the slope of the regression line after treat all policy implementation. And these analyses are also showing a change in the proportion as well as the slope of patients starting treatment right away after enrolling in care following treat all policy implementation. And it suggests here that it wasn't statistically significant, but compared to the counterfactual, it suggests that retention in care was also improving after treat all policy implementation. I'll quickly show just a few more examples of how we've applied this method. This one was led by another epidemiology doctoral student at the time, Ellen Brazier. And here we were looking at the influence of treat all guideline expansion on laboratory test monitoring. So on the top, what you're seeing here is using CD4 tests prior to treatment initiation to see how sick people were prior to treatment initiation. And on the bottom, we're showing changes in viral load monitoring after ART initiation. And I guess the highlight here, in addition to sort of showing that CD4 monitoring has sort of been compromised by treat-all policy implementation, I just want to highlight one of the luxuries of a cohort study like IeDEA is that we can do all kinds of different subgroup analyses. So what we have here is, by age, adults, adolescents, and children, and then within each graph, we were able to stratify by the trend in lower and middle income countries compared with that of high or upper middle income countries. And this allows us to show, the extent of some of the deficiencies in care around the world and disparities that exist between resource-rich and resource-limited settings. And the last example I'll just show is another one that used regression discontinuity in time to assess the impact of the COVID-19 pandemic on HIV care delivery. And this is from 3 West African countries. And they basically showed that HIV clinics in 2 out of 3 of those countries did demonstrate some resilience after the acute onset of the pandemic, as they began to return to earlier levels of ART access, despite challenges of the pandemic. So in conclusion, the IeDEA data we found are incredibly valuable for answering a variety of causal questions, particularly when applying quasi-experimental methods. But looking ahead, a key question is, what are the most important causal questions that we should be trying to answer in the IeDEA network? And for us, one of them is to estimate the influence of extreme weather and climate change on HIV care outcomes around the world. And so on the next few slides, I'll just give a bit of background on this and hopefully convey a little bit about our motivation for undertaking this research question in the IeDEA network. So this slide highlights the burden of extreme weather events around the world, showing here, as well as the how it overlaps with the burden of HIV around the world, particularly in sub-Saharan Africa. I already gave some statistics about, the burden of the HIV epidemic right now, but I guess the takeaway I want to impart here is that the regions most affected by climate change, those that experience more frequent severe extreme weather like droughts and floods and heat waves, are often the same regions where HIV rates and HIV burden is the highest. And this creates a dangerous potential for synergy between the extreme weather trends and the HIV trends. Whoops, sorry about that. And so the impacts of extreme weather events such as infrastructure damage and disruption in healthcare delivery that can occur may directly hinder HIV prevention and treatment services, making it harder for people to access their care, to adhere to their treatment and maintain their health. And this overlap of the impact of extreme weather on populations and infrastructure also threatens, on individuals, also threatens to limit the impact of the public health response to the HIV pandemic. And so we felt that as such, it's really essential to us to understand more about the specific areas of vulnerability within programmatic areas such as HIV testing, prevention of mother-to-child transmission, care enrollment trends, maintenance of treatment, viral suppression, and all the way through the care continuum to retention and care. And by learning about some of these potential vulnerabilities and mechanisms, we can help programs adapt and potentially help limit any negative impacts of extreme weather and climate change on the pandemic. So, climate change is really expected to have some far-reaching consequences, and this includes catastrophic events on human health and well-being, but so many other things. But for populations affected by HIV, the impact could be particularly severe. There was a recent editorial in the Lancet HIV earlier this year that focuses on the effect of climate change on the public health response to the HIV epidemic. Specifically, it highlights concerns about the impact on access to critical services, adherence to treatment, and food security. And some studies additionally have shown that during times of strain, for example, when food security is increased, there can be increases in risky sex behaviors like transactional sex as people respond to the economic pressures that come with the effects of extreme weather. And the concerning part is that while we understand some of these direct and indirect effects, many of them remain poorly characterized. And this gap in understanding really highlights the importance of ongoing work in linking climate and health data in general. And as these insights can be critical in guiding and planning and efforts as well as effective adaptation strategies. So just to highlight the potential scale of the effects of climate on the HIV epidemic, a recent Frontline AIDS report highlights how some of the stark projections in relation to the intersection of climate change and HIV, with modeling estimates from about 400,000 people in 25 different countries, suggesting we could see an increase of 11.6 to 16 million additional cases of HIV by 2050 due to rising temperatures and their cascading effects on health and behavior. And my colleague Sherry Weiser published a paper a while back that highlights and really tries to convey some of the putative mechanisms by which climate change and specifically extreme weather events like drought could influence HIV-related outcomes. And understanding the prevailing pathways is crucial for identifying interventions that can mitigate the impact of extreme weather on people living with HIV. So just to walk you through a few of these pathways, one is, through drought, it can create issues around water and food security. Extreme weather can also cause people to migrate and be displaced. It can increase the incidence of infectious disease, not just HIV, but for example, mosquito-borne illness and waterborne illness. It can erode infrastructure, and it can lead to political unrest and conflict and violence. And all of these things have the potential to increase the risk of acquiring HIV for those that don't have it, and for those that do, increase their risk of morbidity and mortality. So I won't go over the whole literature that we've looked at in preparation for some of this work, but just a brief summary here is that the most of the studies to date have been cross-sectional. They use population representative data, and some of which were the ones that were led by Sherry Weiser and her team that found associations like between heavy rainfall or drought with outcomes such as higher HIV prevalence or more sexual partners, less HIV testing. And there have been some other cross-sectional studies that have linked food insecurity to a higher risk of recent HIV infection. But few studies have really looked at the link between extreme weather and HIV care outcomes, including in longitudinal studies. That is until recently. There's a group that's connected to the IeDEA network that began a study and published a study recently. This was led by Adam Trickey and colleagues that longitudinally examined the association of decreased rainfall during a period of heavy drought in Southern Africa during 2014 to 2016, and looked at the association with subsequent HIV care related outcomes among people on antiretroviral treatment in Southern Africa. And they examined this 2-year rainfall at the location of each HIV clinic compared to historical 2-year rainfall amounts, going back many decades before that. And they looked at outcomes of all-cause mortality, low CD4 counts, detectable viral loads, and gaps in care. And what they found was an association of decreased rainfall or drought, in this case, with higher all-cause mortality in people with HIV and a higher likelihood of detectable viral load as well as a lower number of HIV care risks, care visits as the level of rainfall decreased. And but their main conclusion here is that there's a lot more research that's necessary to understand the mechanisms behind any causal effects that may be operating. So to sum up what we know about the literature then, most studies of extreme weather and HIV-related outcomes are from sub-Saharan Africa. Most of the studies are population-based, but also cross-sectional. Studies have looked at both extreme rainfall and extreme drought. And there has really only been one longitudinal study. Maybe there's been a second one actually, which I didn't have time to fit into the talk. But it's the only study to our knowledge that's looking at HIV care outcomes as opposed to prevalence. So in the IeDEA cohort, it brings us back here again, and the potential role it could play in addressing gaps in knowledge like the ones highlighted by these studies. And hopefully generate some useful evidence for program planning, intervention development, and adaptation to climate change. In many ways, the IeDEA network is well suited to advance this field. First, the geographic coverage is vast, including more than 700 participating sites around 44 countries. And second is it's large, with more than 2.2 million people with HIV enrolling in care at participating sites. And third, the data go back as far as 2004 in many instances. So there's this means that there'll be many extreme weather events and a diversity of such events and contexts occurring in proximity to all of the IeDEA sites over that, now 20-year period that we have data whose effects we can begin to examine using the IeDEA data. I should point out too that in the IeDEA network, we have a lot of unexplained variation in our outcomes, and so a lot of what probably explains that variation has to do with contextual factors and things happening outside the clinics, not necessarily captured in our data. But climate change and extreme weather and seasonality may be one of those things. So it may be that we get some answers about what explains some of the variation in HIV care outcomes in IeDEA by bringing in some of these data. So much of this is really the key motivation for our recently funded NIH study called the Weathering HIV Study. The acronym does hold up. I tried to highlight it here with the letters bolded. And this is a study that's now entering its second year. And its focus is really on using IeDEA data to try to understand the influence of extreme weather on HIV care outcomes. So key to this work is leveraging climate data on temperature and rainfall. And these data are publicly available. They're compiled from weather stations and satellite imaging, which are then sort of interpolated across the globe. I'll try to give you a sense of where these data come from. But they provide data on temperature and rainfall in every part of the world with about a 5-kilometer radius resolution. The data sources have been validated for the purposes of assessing extreme weather events. And this slide is showing you a schematic of a data set called the CHIRPS data. There are many different varieties of these kinds of data sets. We're working with CHIRPS. There's also, that stands for Climate Hazards Infrared Precipitation with Stations. There's also one for temperature as well. And the CHIRPS data were used to create this map here, which shows basically the 3 wettest months of the year around the globe. For example, they're January, February, and March in the countries that are in areas of the globe that are in green, and March, April, and May for the areas shown in dark red. So let's see. I'll see if I can get this to work. Where do these data come from? The slide kind of illustrates the use of satellite technology in generating these data to estimate precipitation. It's critical for our ability to monitor extreme weather events in both real time as well as over long periods. There are 2 main types of satellites that get this infrared sort of energy data. There are the Earth orbiting satellites, and then there are geostationary satellites that kind of rotate with the Earth's orbit in the same spot all the time. The rainfall intensity is visualized in different colors. Light blue indicates light rain, and yellow shows moderate rain, and red indicates heavy rainfall. And these measurements are crucial for these kinds of projects. And they form the foundation of how we track extreme weather events. So over the course of a day, you can see that the entire globe is covered, and this allows daily data on precipitation to be harvested and used. In addition to the satellite data, there's also weather stations data that are combined with the satellite data. These weather stations are on the ground throughout the world, and they also measure precipitation. And so, there are more than 100,000 of these stations around the world that contribute data to this effort. And but it's also clear from the map, you can see that the density and the coverage of these stations is variable and lower in many areas, especially in the global south, so raising the potential for differential data quality. But you find a lot of these stations in places where there are more people. For example, every international airport has them. But the combined satellite and station data in CHIRPS and in CHIRTS provides daily precipitation and temperature data for the entire globe, as I mentioned, at 5-kilometer resolution, going all the way back to 1984. And so we're now in the process of combining the HIV cohort data from IeDEA with the high resolution data on temperature and rainfall in these data sets. It's daily information in both places, right? Daily temperature and rainfall and daily activities happening at IeDEA sites. And this merge using longitude and latitude information of our sites and that in the weather data is helping lay the groundwork for the research agenda, which I'm going to try to outline for you a bit now. So the Weathering HIV R01 grant is a mixed methods R01 study that I'm leading with my colleague Sherry Weiser at University of California, San Francisco. We have 3 aims really, and one is to characterize the associations between extreme weather events and subsequent HIV care outcomes. The second aim is about getting at mechanisms. I'll go into a little more detail in a minute on that. And then the last one is to create and disseminate a country level public use climate data set, because we're finding these data are really challenging to use as epidemiologists and biostatisticians. Just to delve into this, each one of these aims a little bit more. Basically, this is our DAG here. We really want to understand the causal effects of extreme weather on HIV care outcomes. We expect to use quasi-experimental methods to do that work. And for example, we will be able to look at different types of extreme weather events, drought, heavy rainfall, how severe they are, how long they last, on outcomes such as timely ART initiation, viral load monitoring, and viral suppression. And we can see, because of the vast array of contexts in which IeDEA exists, we'll be able to look at how relationships differ by location, as well as the type and the severity of extreme weather events. So as an example hypothesis here, increasing intensity and duration of exposure to extreme weather events at IeDEA sites will reduce timely ART initiation, reduce routine viral load monitoring, and decrease HIV viral suppression. And this is just to give, we're limited to what's measured in the IeDEA network data. You can see some of I've already alluded to a lot of the primary outcomes that we're able to measure. We also have some secondary outcomes. And then there's a little bit of a few things measured to let us get at sort of potential mediators, like the infectious disease pathway, the food security pathway, migration, and healthcare access. And then you can see some of the covariates and subgroups that we can examine using data from the IeDEA network, and also publicly available contextual data, such as World Bank income group or local GDP estimates. And this just gives you an idea of some of the subgroups of interest, that things that we'll be able to examine outcomes, groups that we'll be able to focus on exclusively because we have so many records in IDEA, and also stratification variables. The second aim is about mechanisms of impact that may enhance resilience against the effects of extreme weather events. And for that, this is our mixed methods aims. If there's time, I'll say a little bit about our qualitative aim, but mostly I'm going to talk about the quantitative work, which will be informed by the qualitative work, and we will try to use the data we have to understand the different pathways that extreme weather events are influencing HIV care outcomes. And we haven't started this yet because we are still working with creating the data for our analyses, but we plan to distribute a public use data set. So let me give you an example of how we're using the CHIRPS data to characterize climatic drought exposures at IDEA clinics. This is some of our preliminary work. It's being led by our postdoc, Sophia Arabagis, and also Frank Davenport, who is a health geographer and climate scientist at the University of California, Santa Barbara. So we're just getting into these data and still exploring, but to characterize drought exposure at the IDEA clinics, we use the latest release of the CHIRPS data to derive monthly what are called standardized precipitation evapotranspiration index, SPEI, for each IDEA network site location from 1980 to 2023. The SPEI is a drought index that accounts for both rainfall deficits as well as the potential effects of temperature-driven evaporation, which can reduce the amount of rainfall that's available to moisten soil and to provide water for crops. Importantly, we examined the occurrence of drought for each IDEA site in the typically wet months of the year prior to the growing period. That's when the negative impacts of drought on food security can be greatest. And specifically for each of the 3 wettest areas, we calculated the monthly average rainfall for the preceding 30 years, and we classified the monthly rainfall at each IDEA site in those 3 months of a year as being a non-drought month if the SPI was greater than -1.3, so in this region, as a drought month if it was in that region, and as an extreme drought month if it was an SPEI less than -2. And then we also assigned a drought status to buffer months before and after those wet months. So this is just going to give you an idea of how we're beginning to look at these data. So there are 5 consecutive months in each year that we're working with in this analysis. And then drawing on multi-state modeling theory, we considered the trajectories and probabilities between non-drought, drought, and exceptional drought periods for each site in each year, and derived counts of the drought-related transitions per site per year. So imagine, for each one of these transitions from month 0 to month 1, month 1 to month 2, for each one, there's a matrix that represents a transition. And in this case, from month 0 to month 1, we went from a non-drought condition in month 0 to a drought condition in month 1. And then we can have another matrix for this transition and this transition and this transition, that we can then compile the sum of all 4 matrices and then count the number of drought conditions of interest to us. So it can take on a value from 0 to 4. So we took these data, we did it for every site for those that 5-month period in each year. And this graph is showing the occurrence of drought based on the SPEI at each IDEA site location in each of the 3 wettest months, with the shading here indicating the level of the drought according to the SPEI. So yellow is a lower drought index and red is very severe drought. Going all the way back from 1981 to the present. So each of the 700 plus IDEA sites is represented on this visualization, and it's organized by IDEA region. So we have West Africa up here. This large region is Southern Africa, North America, East Africa. This is the Caribbean and Central American region, Central Africa, and Asia Pacific region. Because the sites in each region can be close to each other, you can discern that there's some considerable overlap in the observed patterns and temporal drought patterns and their intensity, but you can also appreciate the substantial variability even within the regions. And this slide is just an aggregation of that drought data, here showing the cumulative number of drought transition events in the 3 wettest months of the year for each of the 700 sites, with the dark line here. Each of the colored lines represents an individual site, and the dark line represents the average of those sites over time. And using those counts, again, we can see variation in drought conditions between regions and within sites. And within some regions like Western Africa, they can sometimes have very long periods of no drought conditions. So, here you can see, for example, a site that there's no change in drought conditions for maybe a decade. And there's also evidence that some sites where drought conditions may be accelerating over time. But the point here is that we'll be able to leverage some of this variation in some of our analyses with outcome data. At this point, I guess zooming in on the IDEA site locations in Eastern and Central Africa, this is an example of how we can use the data to classify IDEA sites according to their risk of drought, which we did here with using tertiles of the probability of drought distribution. We were able to classify those sites as at higher risk versus medium risk and low risk, map them here according to those colors. And you can see even in some places there are where sites are pretty close together, you can have low, medium, and high risk. And this represents some topography, for example, mountain ranges and things like that aren't visible on this map, but it's definitely something we'll be exploring further with some of our geographic analyses. And lastly, I wanted to zoom in further on the Central African region of IDEA to show some of our first analyses that are linking drought data and HIV care related data at IDEA sites. Specifically here, we looked at the outcome of overall visit volume and the visit volume in each month for each of the 24 IDEA sites shown here in relation to drought as defined previously. And at this point, we've basically just overlaid the data on monthly visit patient volume with drought occurrence, with drought months indicated by the vertical bars here, and the darker vertical bars indicate more severe drought months. It's difficult to infer any patterns or associations from these plots, from these early plots. And the variation of the total visit volume in each month is substantial and likely driven by a number of factors. But it may be that the association of drought with visit volumes, if they exist, are lagged in some way. But before we embark on one or more analytic strategies for this and other outcomes, we'll want to do some more descriptive analyses and review of the literature. But this is just to show you that we finally gotten to the point where we've been able to create a drought exposure measure and to begin to merge it with some of the patient outcome data. So our next steps for this work is to actually embark, and we've begun to do this, on a systematic review of exposure definitions for drought, extreme rainfall, some of the extreme weather exposures that we're interested in that have been used in published studies of extreme weather and health outcomes. We need to better understand the temporal patterns of different extreme weather exposure types at IDEA sites. And there are also many different data sources you can draw on to look at these kinds of exposures. And we want to look at many of them and triangulate and look for how much agreement and disagreement we can see. And then ultimately identify some of the best modeling approaches for the exposure outcome associations that we're interested in. And this likely will depend on the type and pattern of exposures, but of course, the usual suspects of quasi-experimental methods are on the list here. I'll just highlight quickly what's going on with the systematic review that I mentioned. Again, Sophia Arabadis, our postdoc, is leading this effort. But I just want to start by conveying the complexity of the relationship. This is just showing drought as an exposure and, say, adherence to ART medication as an outcome. The complexity of all of the theorized and sometimes documented associations in literature that we need to be considering as we're designing our analytic strategies for this work, and they bridge many different realms from demographic to social to economic. So before we can really understand how people living with HIV might be affected, we really do need to understand more about the nature of the exposure, and that's really where we're working now. And so these are some of the research questions that we're going to try to address with our systematic review. Mainly it relates to exposure measurements. And there's some other things. How do we take into account uncertainty in the geographic environmental data, a lot of which I just showed you. And I'll just go through this quickly because I know we're coming up against time, but we do, I showed you a lot of the quantitative research that we're doing and that we have planned. But of course, we expect to learn a lot by just talking to individuals who are affected by extreme weather. And aim 2 of our study is about using mixed methods. And our plan here is to conduct a longitudinal qualitative study among people living with HIV, as well as key stakeholders in 2 areas of the world that are both affected by HIV and also affected by extreme weather. We plan to understand more about the lived experiences of people living with HIV during recent extreme weather events in these regions, and including the ways that they perceive it impacts their physical and mental health and HIV care access. And we also are going to do key informant interviews to understand, the ways that people are envisioning that extreme weather events are impacting HIV health outcomes. So we'll be doing about 30 interviews in each of the settings. These are some of the themes that we'll be looking at. And we're focusing on different populations in each setting. In Rwanda, we'll be focused on, in general, men and women, but also pregnant and postpartum women, who we believe are particularly vulnerable to the effects of extreme weather. And in the Philippines, we'll be focusing on men who have sex with men and people who inject drugs. And for key informants, we'll be talking to people like healthcare workers, community health workers, Ministry of Health decision makers, and people that work in disaster management agencies and departments of transportation, just to give you an example. So I'm going to wrap it up here. It's my last dystopian looking AI generated image that kind of shows a long road ahead with lots to learn on the way, and hopefully we'll be able to garner some knowledge and insights about the ways in which the world needs to adapt in order to help optimize the impacts of implementation around trying to end HIV as a public health threat around the world, and hopefully at the same time give insights for some other outcomes as well. And I just want to acknowledge just so many people that are involved in this work, from epidemiologists to biostatisticians to health geographers, demographers, environmental scientists, all around a very multidisciplinary effort. Thanks for listening, and thanks for your time today. I'm happy to take any questions.
Thank you, Denis.
I know Dr. Bonetsky has her hand raised if she wants to ask her question.
Thank you. So in the initial work you showed on showing improvements in HIV outcomes after guidelines, which is as you would expect. So that it was nice to see that. I guess things that change over calendar periods that could potentially, one would say, you may see the same effect if education was increasing in that country. So I think you said that in your IDEA cohorts, you've got information on education and employment and so forth on a subset. Is that right? Because if so, I was wondering how you're going to use that to improve the quality of your quantitative analyses.
Yeah, so we do have in a small subset of IDEA sites, there is more data collected, but for the vast majority, we don't really have good socio-demographic data other than age and sex. But at the same time, many of for some of the extreme weather events, the time horizon is really quite short, and I wouldn't expect to see major changes in some of those secular trends in things like education. But for things like drought, I suppose they can be quite protracted, and it could happen. But I think the one of the strengths that we potentially can bring to this is looking for similar effects in multiple settings around the world, where there would be more random variation in education trends than and the focus could be more on the extreme weather events, if that makes sense.
Thank you, Dennis. Thank you for an interesting talk. And I just want to do that because I know we're kind of short of time, and I'd like to acknowledge you before it's too late.
Nandi, do we have one last quick question?
Yes, please, Haroshi, please take over.
Yes, because we have a student. You can speak to the.
Okay.
Yeah.
Hi, thanks so much for this talk. This is really interesting. My question has to do with exposure definition, and I know that you talked a bit at the end that this is complex and evolving, but also just acknowledging the diagram that you showed showing that there's just so many different mechanisms that are kind of operating to relate extreme weather with HIV care outcomes, but it looks like right now on the maps that you showed that you're defining your exposure based on that, like the point location of the clinic or of the care center. Is that correct?
Yeah, we are. For example, with drought, it's based on a radius around the care clinic. Yeah.
Okay, because I think that's what I was curious about, is just if you're thinking just in terms of mechanisms, that it's really what's happening close to the care clinic that is driving or that would impede people seeking care, or if it's more kind of like broader area level droughts or rainfall or different things like that that would affect care.
Yeah, so certainly agree with you. The complexity is daunting, but there are a couple of different approaches we can take. Let's take drought, for example. So there can be drought happening at a clinic or not, with food security still affecting, with drought still affecting food security around in the patient population there. For example, there can be a drought in Nairobi, but if there's not a drought in the food growing areas that supply food to Nairobi, it may not be such a food security problem. So we also need to be thinking about the ways in which the drought in the areas that are providing the food to another geographic area, just to add a layer of complexity. Yeah. It's just to say that we're not only looking around the clinic, but we're trying to take into account the larger system of the food supply in many locations when we look at these measures. Right.
Sounds cool. Thank you.
Thank you. Are we done, or can I ask one more question? We have another student who wants to ask a question. You can come up and speak because I don't have a microphone in this room right now. So
yeah, go ahead.
Okay, thank you, Randy.
Hi, thank you for the very interesting talk. I have a quick question about when one chooses a regression discontinuity design over an interrupted time series from the first half of your discussion on treatment eligibility expansion and its impact on timely initiation. So we do look at the threshold and the slope, the threshold jump and the slope in both the designs. What dictates the choice between the? Over to you.
Yeah, great question. I think we've used both to examine the same outcomes in Rwanda, the example I showed, and each showed a similar result. I think, you know, it often comes to a question of like what form the data are available, how many trend data points you have, you know, to be able to use before and after, how well defined the exposure is, or the point in time where the exposure of interest is happening. So I think it's a number of factors, and in our case, we would initially thought we'd be using regression discontinuity, for example, to look at the effects of extreme rainfall, but it's because of the way that exposure works, there can be multiple events happening in succession in a short period of time, and it's not the best approach in a situation like that. And for this, like, and I can say less about this, but my colleague Zach Shan at CUNY is encouraging us to think about things like structural nested mean models that allow a little bit more ability to look at the effects of flipping the intensity of something up or down over time on outcomes. And drought is another one that he hopes to apply the method to. So I don't have a clear answer for you. A lot of it depends on how much trend data you have, and how well characterized the exposure is, and if it's repeated over time. Regression discontinuity in time isn't, especially at close intervals, regression discontinuity in time isn't necessarily going to be the best bet.
Thank you. Do we have any other question?
I wanted to ask a question. Hiroshi, you might have a question. I'll encourage you.
You could go ahead, but I have one last
Please.
question, but
Okay, please ask your question first. I'll
okay.
keep mine for the end.
Thank you. That was great. I just have a quick question about your Z distribution of drought SPEI index. If you in one of your last slides, that the SPEI index standardized is like country specific, is it? You construct those extreme droughtness index for each country?
It's even more specific than that. It's location specific.
So it's subnational estimate.
50 kilometer radius or 5 kilometer, you can specify.
I see. Because I was just thinking, if it's country specific, if one ever wants to have absolute magnitude of droughtness, however people measure, it's not comparable across monitoring location. Is that correct? That distribution is only useful for each site? Because it doesn't encode absolute droughtness intensity once you standardize. Is that how it works?
Yes, if I'm understanding correctly, the amount of rainfall or lack thereof for two different sites can mean, if it's the same, can mean very different things for the site because their historical conditions can be different. Yes.
Okay, great. That was my question. I'm done, Nandini. So thank you.
Thank you, Dennis. I hope you can wait for one more question from me.
Of course.
Okay, thank you.
Yes.
So I was curious about that first set of analyses that you presented. The previously eligible group of people for ART didn't, you didn't find any difference in that group when there was a change in the guideline. There was a small difference for when the guideline expanded to the 350 threshold, and then a larger difference when you went to the 500 threshold.
Mhm.
I was just wondering whether you also looked at the non-eligibles. So for example, you take that first point when you expand, when there was an expansion to CD4 less than or equal to 350, in a sense, the non-eligible people are also a kind of control group. And it would have been interesting to see what happened in that group. You know, you'd ideally expect that there's no change over there. I mean, that would be reassuring. If you saw that there was a change in the non-eligibles as well, then, you know, that might suggest that the expansion is, or the impact is not because of the guideline, but because physicians are maybe just treating people anyway, irrespective of the guidelines in the categories with higher CD4 counts.
Great point. I agree, and it may be that we did examine that group, but I'm going to have to go back to that original paper and look. But yeah, we only presented those here that we would expect to initiate treatment under the guideline. I should say also that our ability to measure, so eligibility, this is a messy part of the work, but eligibility isn't only dependent on CD4 count. So someone can have a CD4 count of 550, but if they have an opportunistic illness, they'll be eligible. And we didn't always have the best data on opportunistic illnesses. So it's the categorization is a little bit messy, but I agree. We can certainly go back and look to see if we did that. It would have really added to the story here.
Thank you, because I think that would strengthen the analysis. Like some of the trends you showed in plots subsequent to this show that clearly the ART usage is increasing anyway, irrespective of the guideline in some countries, not all, but in some countries. So I think that would add a little bit to the impact of the, your ability to measure the impact of the guideline itself.
No, fair point. And I probably didn't say it, but I viewed these two groups as what was likely going on with the secular trend in ART initiation. So it was kind of steady under this expansion, but it actually was increasing a bit from, this is what, like kind of like a counterfactual, what would have happened to if the policy hadn't changed. And so this whole difference we're seeing here is not due to the guideline. I think you have to subtract out what was actually going on in the background.
Okay. Thank you very much. I guess we'll close there. Hiroshi, are there any further questions?
No, I think we are mostly done. So thank you very much, Dennis. It was impressive.
Yeah. All right.
Thank you for having me.